Good morning, good afternoon, and good evening to those of you who are joining us from across the world today for another edition of Pandemic Punditry brought to you by the Content Experience Company. We are delighted and honored to have with us Professor Ranga Dias, Assistant Professor at the University of Rochester, New York, who is credited with creating the world's first first room temperature superconductor. So, welcome to Pandemic Punditry, Professor Dias.
Thank you very much. Thank you for inviting me. It's a pleasure to talk with you.
Well, you obviously what you've done is a sort of a historic first. So we want to sort of get behind what exactly you've actually done in this area in superconductivity. But before that, I was just wanting to sort of get a sense of what your personal story was, how you came to be where you are at this sort of historic moment in time.
Um, well, definitely. I mean, I'm originally from Sri Lanka, and one thing I wanted to really mention is that when I was a little kid, I was so much into astronomy. It was like a sort of the field, observational astronomy. And when I was 8 years old, I joined an astronomy society in Sri Lanka called Astronomy and Space Study Center. That was a place like undergraduate, high school students, faculty members, and everybody get together in a Saturday, like have a workshop type of every Saturday. So it doesn't matter which age group you are, you can participate and you can learn things. So then in the morning session, we have astronomy lectures, and the afternoon session, you have sort of like a science discussion. So that's where a lot of physics and engineering, came to the picture. Even when I was very young age, I was sort of exposed to these, terms. I have no idea at that back then what are these things they're talking about, quantum mechanics and things like that. But that kind of gave us a little bit of curiosity to learn a little bit more deep into these pure sciences. I think that was the foundation that always put me into this direction to explore this being a scientist, that sort of mentality. And then I joined the University of Colombo to do physics, and there I did my PhD in Washington State University in physics again. Then I joined for postdoctoral studies at Harvard, and then I came here to have my independent research career at the University of Rochester. I think this the foundation that I got in this Astronomy and Space Study Center was, I would say, the key to this where I am today. Yeah.
Wow, that's a really fascinating story. Do you know whether the same society still exists in Sri Lanka, and that young kids?
We're still having not the same level that we used to. I think it's like last 5 years is sort of like a slow it down a little bit. But this was started in 1980s. It was very active in 90s and 2000, even in up to like 2015. Then most of us are now old, and we all like sort of scattered now in different countries. But we get together. We still get together and share our our memories. It was the best time of our lives. Yeah.
Oh wow, it's amazing how those small things when you do at a young age imprints so strongly that and you are talking and to the rest of the world about some incredible achievements. Kartika.
Thanks, Lavi. Professor Dias, thanks for joining us today. It's absolutely fascinating, and congrats on making the Time 100 list.
Thank you very much.
Found you. Before we sort of really dive into the geeky part of everything, could you tell us why it was important to have superconductivity at room temperature as opposed to the high and low temperatures that it was sort of operating in before?
Yeah. So the one of the property of if you take a normal ordinary metal, if you send a current, you will feel that it'll get heated, right? Let's say, for example, your hot plate that you in your kitchen, your range topper. So you get the heat to cook your food because of the resistance of these metals. That means that we lose a lot of energy for this resistance in the material. Imagine now if you can have a material, a metal or something that you can send the current without any loss in electrical current. So you can have without any power dissipation, no heat being dissipated because of the no resistance. So this means you save enormous amount of energy. So the material that has no resistance we call superconductors, and we found this material 1911 when we study metals under low temperatures. We saw that around like 4.2 Kelvin, all of a sudden resistance disappear. This was like a first observation. But since then, these observations always happen at low temperatures. And if you wanted to make an actual practical use, not having any resistance in a material. So to give a little bit of examples, like if you wanted to send a current from, let's say, from one end to point A to point B, so you use this transmission line. And when you send the current through, you lose energy, and then you're not getting the full efficiency of this power grid or whatever you're using to transform the energy. So you lost enormous amount of energy. For example, in US, you lose like 200 million megawatt per hour electricity just because of this resistance. And if you convert this to a dollar amount, it's $20 billion. So, but if you can have a wire or transmission line made out of superconducting material, which doesn't have any resistance, then we will get the full the energy transfer from point A to point B without we loss. So this can power 23 million more houses in US if you can have this wire from superconductor. But then all these nice features happen, the properties happen at much lower temperature. So then the question is that in order to get actual practical use, you need to bring the temperature, room temperature, so that we don't need the cryogenics or other things to make it cool in low temperature. For example, we have to use liquid helium, and as a planet, we are losing liquid helium. So the cryogenic cost for the cryogenic is expensive. So at some point, we can't sustain these low temperatures. So you need something that can operate without the assistance of the low temperature. So that's why it was so important to have something room temperature or above room temperature, so that we don't need these cryogenic. I mean, give a little bit of more detail. MRI machines we use in the medical imaging system, they use a superconducting magnet, but they use these cryogenics to keep these superconducting material superconduct. Because at room temperature it doesn't work, so you have to cool it down. So you use the liquid helium. So that's costly. But imagine now if you can have a superconducting magnet with room temperature, then you don't need any of these cryogenics. The cost for MRI machines will dramatically reduce, and even the third world countries can be afford more machinery. It will like an upgrade, right? So the point is that it's always being a low temperature phenomena. So you, in order to get actual practical use of these material, you need to raise the temperature to room temperature. So that's why more than a century, people keep pushing, all the scientists, keep pushing on this problem, how we can bring it to room temperature, because of this technological advantage we can get having these materials. Yep.
Wow. So I learned two new things there. I didn't know the MRI machines that I've been into several times actually used cool superconducting.
Yeah.
That's new. I didn't know that. So that's amazing. And the other point you made, which is also something that caught my attention, was we're losing helium. Why are we losing helium?
I mean, it's one of the lightest gas that as a planet, so it's easy to escape. So it's helium, yeah, like hydrogen. So it's just, as a planet, generally we're going to lose it, and we have to liquefy it, right? We have to put into the system and then make it liquid helium to get into the low temperatures. So if you don't have enough gas, then we can't make it enough liquid helium. So that's the biggest. Yeah, at some point we will lose helium.
Okay, and that's because there's a finite amount. There's a finite amount in the atmosphere, and we're using it for like MRI machines and other things, and and balloons and everything else. And suddenly,
at some point we have to think about some alternatives. Yeah.
Okay. So, Professor Dias, I understand that I'm just giving you sort of, and please correct me if I'm wrong in this description, but I understand that your team first sort of mixed carbon and sulfur in a 1-to-1 ratio. Then you mill the mixture down into tiny balls, and then squeeze those balls between two diamonds while injecting hydrogen gas. And then a laser was shined at the compound for several hours to break down the bonds between the sulfur and the atoms, thus changing the chemistry of the entire system and the behavior of electrons in the sample. This created a crystal that is not stable at low pressure, but is superconducting. and it's also very small. Did I describe sort of your process accurately
Yep,
enough? Please
absolutely.
correct me if I'm
Spot
wrong.
on. No, that was spot on. That's perfect.
Okay, and this is tiny, right? This
Yeah,
conducting crystal that you created was
yeah.
how
The
tiny is it?
So it's like I would say 1/10 of probably, yeah, 1/10 of the size of your hair, the diameter in terms of, yeah.
Wow. Okay.
This is very small. Yeah.
Okay. This is not something it was visible to the naked eye when you were sort of
No,
doing
no.
this.
You need a microscope. Yeah.
Okay. Okay. So all right. So what was your initial reaction when you were doing this experiment and it started to superconduct, right, at room temperature? I mean, what was your reaction, if you could share that?
Oh, well, yeah. I get this question a lot. To be honest, I mean, I didn't believe it. When I first
Okay.
saw it, I was like, "Oh, this cannot be true." It's so good to be true, or something, some sort of that order. So then we did like so many other experiment to verify that, okay, this is actually, we are seeing a superconducting transition. You can do other sort of experiment like magnetic field studies, some magnetic measurements. There are a few ways that you can verify that. So we were like, day and night, okay, we need to make sure that we were sort of, think of this way, we were trying to prove us wrong what we are thinking. Okay, so then all the other experiment we did, they converge into, no, it is superconducting. And then sort of like a eureka moment, okay, that's it. Yeah, we were very
So
yeah.
what was the delayed reaction then? What was the delayed reaction after you put your scientific hat on and verified everything? Were you guys jumping up and down in the room? Were you screaming? What was
Yeah,
the...
we were like, yeah, so yeah, it was just like, oh wow, this is like, I mean, one of my colleague that who work on this one, I wouldn't say the name, but he was almost trying to mimic the eureka moment, taking off his clothes and running on the department. Because this is midnight. It was like 11 somewhere around 11:30 in the night, so nobody's around.
Oh, that is brilliant. So you're saying that you're still trying to discern the actual composition of what it is that you created. So I remember this when I was learning the scientific method, or this history of science, we had alchemists, right? These people who sort of mixed together various chemicals and made things go boom and bam and whatever, and then created things. So this is almost like alchemy, right? I mean, you've sort of created something that just sort of happened, and now you're trying to sort of unpack it and figure out exactly what is it that you've created. Am I oversimplifying that, or am I accurate?
Oh no, no, no! You're absolutely correct. Yes. So we made this material. I mean, we can see all these properties, superconducting, everything, but the exact structure and the exact stoichiometry is unknown. So the one of the problem for that is that in generally in a high pressure, I mean, in physics, we use X-ray diffraction to understand that. What the crystal structure, what give rise to these, how the atoms are arranged in the given material. But if you have a lighter element like hydrogen, it's the lightest material that we know, and carbon is the same, not that far, and sulfur as well. So then, if the X-ray diffraction, the quality of the data is depending on how heavy the material you have. So being a lighter element is always sort of a disadvantage to get a better quality data that we can sort of nail it down. Okay, this is the structure. So that's the drawback. Sort of like we are struggling here to understand what's happening there. But we are developing some new technique to sort of understand this local structure. Hopefully, we'll be able to get that thing sorted out, because that's very important even for theories. So that they can understand the mechanism, because not knowing how the atoms is arranging, it's sort of difficult to, we can guess, we can do all those calculations, but knowing it exact structure is very, very important. We did some other spectroscopic techniques, or like Raman spectroscopy, that sort of give you idea, how many atoms are there, what kind of how they vibrating and things like that. But still, it's not like very conclusive evidence to say that, okay, this is what we have. Yeah, this is probably will take a year or two to finish it up. Yeah.
Oh, wow. Kartika?
Thanks, Navid. So, Professor Dias, if you look into the future, like 10, 15, 20 years down the line, and with all of the problems that we're facing right now with climate change and trying to reduce emissions and all of the stuff, what impact do you feel like this new, discovery that you've made will have on mankind?
That's a great question. Yeah. Well, I see. So let me, if I break it down, let's imagine that we can one day we're going to have a room temperature, room pressure superconductor, so that we can make a wires or whatever we know. We will come to a point that if you go to the store and then you want to buy a spool of wires, then the owner of the store gonna ask, oh, you want a superconducting wires or you want a normal wires? If you can get to that level, and then the application wise, I can categorize to four, like in energy and the technology, transportation, fundamental science, and the medical sciences. Those four areas will have a direct impact because of this material. Then if you go to the energy, the one subsection, energy and the technology, and with having a power grid, without any loss in transmission line, that's great. But then let's say we wanted to push for the solar energy, we want to push for electrical cars, electrical planes, and things, so that we can reduce this emission. And then think of all these circuits and everything electronics that we have building there with the semiconductor, which we have a loss in power, will replace with the semiconducting circuits, semiconducting wires and cables. This will give us advantage of saving the energy, and then you may have an increased range in your electrical vehicles, and then even the portable electronic device you're using maybe have increased lifetime in the battery life. And then the transportation, even the airplanes, and so many things you can think of that will revolutionize such a way that we don't need to use these other sources that can harmful for your climate or you as a planet, for whole the area in the planet. So this will sort of it will upgrade all the existing methods that we're using, even technology or transmission or fundamental science or even the medical imaging systems, into a different level. Like I always say this, like we can go from semiconducting society to sort of like a superconducting society, and then we can operate without any power loss and circuits. And I think the solar energy, the usage, the solar panel, the efficiency will dramatically increase if you with the superconducting material. And then the transportation, electrical vehicle, electrical planes and things, even the rockets, for that side of it, will dramatically increase the lifetime of batteries and the range and everything, and the fundamental science. So this will have a direct impact into the energy, the clean energy. So we call it green energy. So that way, I think having this material and ambient pressure, ambient temperature will definitely benefit for all of us. Yeah. So I think that's why I think so many scientists were really pushing for this, because they see the change that we can do having this kind of a material in existing on Earth. It's just like if you watch the movie Avatar, there's unobtainium, right? They that's what they were they were looking for, something like that. Yeah.
Karthika, any more question on follow up on that or?
I have a follow up. So with people like Elon Musk, trying to go to Mars, and Virgin and all those companies doing Hyperloop transportation and stuff, how does room temperatures, semiconductivity sort of impact those technologies?
This transportation will definitely, there's the boring company that he's making this hyperloop, right? It's like a friction. So one of the property of a superconductor is that if you let's say you have a superconducting material, and if you apply a magnetic field, instead of this field goes through the sample, it goes around it. Sort of this will make it levitated, like you can lift it up. So we call like a magnet, there's a quantum locking there. So then, which means that if you have a room temperature material that can operate at superconducting material at room temperature, then you can have these magnetic levitated trains. This technology already sort of practiced, but again you need a cryogenics. But if you remove the cryogenic factor, and if we can have this one at ambient temperature, then you can have frictionless trains. So this will increase your speed and the transportation, the efficiency of it. So the companies like Boring Company, that what they're doing will definitely impact with having a superconducting material. And in terms of space, aerospace engineering, I would say it's the same way. Changing all the electronics to superconducting material will definitely reduce the mass and reduce the efficiency. There's no loss. This will get lightweight rockets, and this will sort of give you advantage. You may at some point may not need a two-stage rockets. One interesting thing about this room temperature superconducting, especially the hydrogen. So the pure metallic hydrogen predicted to be a room temperature superconductor. And also this material comes with this, it's a high energy density material, and it can use as a rocket fuel. And instead of using liquid hydrogen and the oxygen, if you can have a metallic hydrogen as a rocket fuel, this is a lightweighted fuel that you can ever, get, and then has a enormous amount of energy release, much more than what the CO oxygen and liquid hydrogen can get you. So then you can have a single stage rockets. Right now, like for example, in order to go to Mars for Elon, their SpaceX, they need two stages. First, they need to get their Starship to the orbit, right? And then use the next to go to the Mars. So you probably don't need the two-stage rockets. Probably single stage may be enough. So in that sense, I would say forget Mars. Maybe we can go to Jupiter. I know it's too ambitious, but
you might get a call from Elon Musk now.
It's actually mine. You know what? I'm gonna tag him.
So we do have one question for the audience is asking how many variations or fact checking did you do before you sort of celebrated? How because I said you finally celebrated at midnight, so you must have done this over the course of a couple of days.
So the zero resistance, vanishing the electrical resistance is the one property of superconductor. But the other property that I was explaining is this magnetic field.
Right.
So that called with perfect diamagnetism. So you can do the magnetic susceptibility measurements, which tells you that okay, you're going through when it transforms to superconducting, you see the diamagnetic signal. So that's this one method to prove. Then also external magnetic field, and generally is hostile to superconductivity. They destroy the superconductivity. So if you have high enough magnetic field, external magnetic field, you can completely destroy superconductivity. So what we did was we apply external magnetic field, and we saw that the transition temperature shift to so sort of like suppressed to the lower temperatures. And then that kind of lead us to extrapolate that if you have like a 60 something above Tesla external magnetic field, the superconductor will completely disappear. So that's another way of nailing that okay, this is superconducting. So those are the two main other experiment that we did. And also we did isotope effect. We call that if you have a hydrogen, right? If you replace hydrogen with the heavier atom, let's say deuterium, the isotope of hydrogen, and because of the heavier mass, the vibration can get a little bit difficult, so your transition temperature be much lower than the pure hydrogen with the hydrogen in the material. So we call this isotope shift. Because of the heavier atom, you're difficult to move. Think of that way. When you're lighter, so maybe you can vibrate very much faster, but with the heavier atom, it's difficult. So then you will see the shift in TC, like a lower temperature. We did observe that as well. So those are the few experiments that's kind of give us a confirmation that it is superconducting. Yeah.
So I think I heard three there. So all right, so three potential variations, and then
Yes,
then you were able to celebrate.
Yeah.
You said room pressure. I think this is a point that so one of the things that the current constraint is, in addition to being sort of small, is that it requires a lot of immense amount of pressure to create this conductivity. So what you're aiming for is to make it sure that you can actually do it at room pressure. Room temperature, room pressure, superconductivity. That's the sort of the next goal, right? I assume. For
absolutely.
Yeah,
absolutely. Yeah, because what we did was, we sort of used the pressure as a tool to manipulate the molecular level so that it can get this superconducting state. But then, what happens when you release the pressure? Does it goes back to the original form, or can we make it stable? And if it doesn't stable, what are the ways that we can stabilize this? Or is there any other similar type of material that we can come up with which can mimic the same situation but much lower pressures or ambient pressures? Because as I said, it is very important to have something at room pressure and room temperature. So we are actually working on right now to to understand what's really happening in this material, and then see what are the other ways that we can think of to bring this pressure down all the way to ambient pressure. We call something like chemical compression. Maybe that's something to use. In a simple terms, I think of this way. So you're sitting in your room, you have some empty space in your room. You can bring all four walls closer and closer. Then you feel that you're getting packed, right? Your space is getting reduced. This is what, when we press in a material, that's what happens. We call mechanically pressing it. But then let's say if I put 10 people in your room, then again, you feel a little bit packed, right? Your space is getting packed. But then what if I replace these 10 people with some athletic, big, football players or rugby players, the big and 300 pounds, and 10 people, that's definitely you're going to feel squeezed, right? So instead of bringing your walls together, maybe by adding something into, perturbing your original material with the chemical substitution, we may be able to feel the same pressure, but you don't need to mechanically press it. So that's maybe one way to go for it to bring the pressure down. Those are very conceptual still, but we'll see how it goes. I always try to think that we are right around the corner. We are very close. That's how at least we motivate ourselves.
Obviously, and it seems to be working so far. Karthika, do you have a question or a couple more?
Yeah. So if the Boring Company were to call you, if Elon Musk would call you, right, and say, "Hey, I don't care what it takes. I'm willing to fund this. I need this technology. How quickly can you get it to me?" How would you answer that?
Well, so let me put it this way. I have already company formed. So I started a startup company called Unearthly Materials. So the main focus of that company is to make this superconducting material at ambient pressure and ambient temperature, with the focus of have this technological advance what we know. One is transportation, like something like Boring Company is doing, and energy, clean energy, solar panels, and space travel, and all it goes to all these categories. So that's the main focus. Well, if you want to fund our company, I wouldn't say no. Of course, I had to talk to my co-founders, but yeah.
So, Professor Dias, so are you saying commercialization is what, 5 years away, 10 years away, 15 years away, or still unknown?
That's a very good question. Well, yeah, okay, let me. So, the first discovery of superconductor was 1911, and since 2014, nothing. There were some discoveries along the way, but we were always in the low temperatures. It's a liquid nitrogen temperature. That's where we were sort of getting to work.
Go ahead.
Yeah, but then last 5 to 6 years, all of a sudden we went from these low liquid nitrogen temperatures to 200 Kelvin, 250, and 290. So we were like last 6 years like a huge increase. It's like a rocket ship, right? It's just an unbelievable improvement in the last 6 years. If you go on that similar projection, we may be very close, maybe 5 years, 10 years away, compared to the last 100 years. But again, you never know. It's hard to predict. As I mentioned, I always tend to think that we are right around the corner. It's just like almost there.
It could happen tomorrow in the lab, right?
Exactly. That's the thing. So it could happen, yeah, absolutely. It could happen in tomorrow, and it could happen in 5 years or 10 years. But we're gonna get there. At least that's.
Love the optimism of that statement, and I truly value that. I think that's really a positive way to look at life. So, Professor Dias, in your sort of quest to sort of do this, and you shared this earlier, you did all of this in the middle of the pandemic, right? With lockdowns and social distancing and everything else. Um, and so you must be hoping that things normalize quickly, because you were telling us earlier at the start of the show, before we kicked off, that um, you had to actually have these rotations in your lab. You had to have only a certain number of people there at a time. So I mean, this must have sort of impacted your speed to sort of discovery quite substantially, I'm assuming. You must be hoping that with vaccination and improvements hopefully coming around, that your lab time won't be restricted anymore from a pandemic. I'm assuming that's a
Yeah,
concern.
absolutely. Yeah, that's very crucial for have a smooth operation in a lab. So it's getting better now, but at least I think I would say the 2020 in general, it was a hard year for all of us, right? I think maybe there are some positive things came out even that year too. Having this material and some other discoveries that other scientists have done, maybe put the foundation to maybe bigger discoveries in the future. So we'll definitely, with the this vaccine and everything, and increasing the lab time, this will definitely help my lab to increase the productivity. I'm sort of now expanding my lab as well, so that we can look into more material and come up with the different ideas to make it happen at ambient pressures. Will definitely help not having the pandemic.
Restrictions on you.
Oh yeah, yeah.
Yeah, Kartika, any more last questions before we wrap up?
I was just wondering, Professor Dias, obviously hailing from Sri Lanka, whether you are specifically, once you would reach commercialization potential and it's at a mass scale, are there specific emerging market problems that you're looking to solve with your new technology?
So the medical imaging probably the quick impact, because the technology is already there. We're using superconducting materials. It's just changing from cryogenic and not using cryogenics. So that's something easy upgrade that you can do. That will have immediate impact and cost wise and everything. And the other one, the transmission line, the power grid, that will take a while, because you really need to make a wires in that scale. It's a sort of a scalability problem there. But in the small scale, electronics, consumer electronics, or solar panels, electric vehicles, that can have an impact, because if you can print these material in a small nano scale, these circuitries, that even in your smartphone, and if you look at it, you have so many, electronic devices inside this, that can have a quick impact as well. So I would say the clean energy wise, solar panels, electrical vehicles, electrical planes, and things like that will have an impact. And then next goes to this transmission line, and then for the transportation, like magnetic levitated train, things like that. Immediately, medical imaging system will definitely have impact, reducing the cost, sort of upgrade, and then the clean energy side will have a definite impact, and so on. It's not just you may need to have having a room temperature, room pressure is great, but then some superconducting material may have a different type of properties, in the sense that they may have a lower critical field, critical current. So for example, if you wanted to use for this high magnetic field or the transmission line, you need to have a high critical current density. So some may have low, some may have high. So having a one room pressure, it's great, but we also have to have these other properties in the right conditions to get actual use of it. So it's sort of like still going to be a development. But for these consumer electronics, and then MRI machine probably be easy to impact in terms of commercializing. Yeah.
Well, thank you, Professor Dias, for sort of making such a very, very complex subject sound so simple in some sense. But the impact and implications are quite dramatic, I think. So I thank you for joining us for this sort of wonderful conversation. Proud to have talked to you, and for all your accomplishments. We are looking eagerly to see what comes next. And I love your name, by the way, for the company, Unearthly Materials. I was just thinking while you were speaking that, wow, that sounds like an alien material, and then you name your company that. That's very aptly named. So thank you for doing this chat with us. I hope we were able to sort of shed more light to the amazing discovery that you've done. So I'm assuming that you've got this new lab, you've expanded, you're looking to sort of get behind what this material is going to do and how you can make it more sort of more usable, less ambient pressure, I guess is the technical word, and stable and at scale. So we wish you all the very best in that endeavor, and please keep us posted, and we'd love to have you back if there's a new discovery that you want to tell the world. So we'll be happy to have you. Kartika, any last words from you?
No, not really. I was just thinking, with stuff like this, it really does look like perhaps we can save the planet.
Yeah, that's right. Yeah. So thank you very much for inviting me. It was a really pleasure to talk to you both and share my research. And I'm happy to discuss in future discoveries as well.
Absolutely, Professor. Thank you so much for spending an half an hour with us and educating me. I didn't know. Next time I go on an MRI machine, I'm gonna take a Professor Dias. In addition to MRI machines and I think some power generation equipment, where else is superconductivity currently used at cryogenic temperatures?
Yeah. Oh, yeah. Power generators, motors, the frictionless motors, and even the transformers, fault current limiters. There's so many applications. That's why, I always tell this one to my students: the world as we know it will dramatically change if you can make this material. Yeah.
Right. No, but currently it's in MRI machines. It's in some power stations.
Oh yeah.
In a few selected places like that.
Oh yeah. That's right. Yeah. With the use of cryogenic, absolutely.
Right, cryogenic. Okay, great. All right. Thank you very much. All the very best, Professor.
Thank you very much. Yeah. Thanks again. Yeah.
Take care. Bye.
Yeah.